Welcome. I am going to show a, brief introduction to this programming language I've been working on for quite a while now. Go through this presentation and probably show some examples afterward. Let me just pull up something. Where does Twitch even put this? Oh, there it is. Okay. There we go.
Action detected at the front door.
Okay. So I'll be showing you a little bit about this programming language I've been working on for quite a while now, which I've chosen to call the Y programming language. There are quite a bit of features. I mean, anyone that's programmed knows, especially in, I'll say more modern programming languages, tend to give you some nice things to work with, yet older languages such as C, you have to work with, say, like macros to get some things working. But just go into the features and explain a little bit more later. So some of the main features, of course, we got portability, a really nice feature. Anyone who programs in Java knows this. Being able to just use the program or intermediate on another system is a huge boon for even release, just being able to release a program. Explicitness, this is something that a lot of languages, really the only language that is mostly explicit is even the assembly languages. Especially like interpreted languages aren't explicit at all. But I could go into these for quite a while, but I'll just keep going. So type system, I have a completely different type system than I think any other language out there, which is really great. Show the features of that later. And efficiency, obviously everyone wants programs to run quickly. We'll see that. So portability. Now with the Y programming language, with the Y compiler, the YCI, which I've been working on a little bit. I've mainly been working on the design of the language. But with the design of the whole language as the language is and as how it compiles and is run. So Y compiles to an intermediate language, probably using some type of bytecode, or you can compile it to a binary, and the intermediate file, of course, you can then interpret that on any system, or you can compile that to a binary. So you get the advantages of portability, but you can also actually have a native binary on your system. And of course, this will allow developers to compile programs to just a single intermediate file, or you can have multiple intermediate files if you, say, have a library that you're working on, and then you have another program that's using that library. Then you could link that library loosely, so that you still have them as two separate files, but they can still compile to a statically compiled binary. And there's efficiency stuff like removing things that aren't used that allow this to really shine. So yeah, basically you compile to a single intermediate file or multiple, depending on what you're working on. But for the most part, the idea is if you're working on a program, you can compile to a single intermediate file and then just release to the users of the program, and then those users can just interpret it or compile it to a binary. And the specific reasons that this, well, obviously you would want this as a developer, but as a user, in the YCI it's going to be really easy. It's going to compile to a binary as the default. So in whatever system you're working on for those intermediate files, I'll set up the YCI as the default for that, and in the actual YCI it will just compile whatever intermediate file that it's given as a default, and then the user can just run the binary from there. So explicitness, of course, this is a feature that I program in mainly C or C++, but I also program in x86 assembly, and unfortunately C nor C++ maps well to x86 assembly, and because it's not really designed to do that, or at least I've never seen it in anywhere that it's supposed to map directly to assembly. In C, it's more of kind of a notion of this is what the program's supposed to be, and then the compiler goes off and makes a program that can maybe somewhat resemble that, of course, depending on optimization levels, at least with GCC. And I think Clang, I know Clang has optimization levels, I'm pretty sure, but I don't really use Clang, so. So the whole point here is to make it that when you say something in Y, it will do a specific thing with in the actual assembly if it's, you know, compiled to a binary. Although in the interpreter, it will still do the same thing, but of course it has to go through interpretation. So this is really not, like, unless you know assembly, any of the assembly languages, which currently I'm going to be going for probably x86 assembly and ARM assembly, as at least the first two. So this feature is not really something I can show you unless you know these assembly languages and you want to compile to assembly and look at the actual assembly. But some examples of what this gives, and how I've designed around this, I should say, is that the basic type vector will just use vector operations instead of needing to use compiler intrinsics with like C++ or C to actually do a vector operation like VP add D. I think that the size comes after the VP add. It's been a while since I've looked at the actual ISA. But basically just doing all of the actual vector operations, vector adds, vector dot products, vector cross products, just actually as a part of the language. And personally, even, well, with these two things that I have listed here, of course that, and then the circular shifts, or rotate instructions, roar and roll in x86, giving that a specific operator, these two are basically gripes I've had with, well, C, basically. But I've implemented a vector type in every language I've used, I'm pretty sure, and actually just having a vector type, that alone, I put it in here just to have a vector type, but also because then I can just make it use vector operations, and it's explicit, and it's much better than other methods of using vector operations, at least in lower level languages. But going on, so the type system, why I've created quite a complex type system for Y. So first things first, all the types in Y are in a hierarchy. The highest type, or root type, in Y is DT. Just those two letters. Of course, data type. But this is the highest, or root type. It doesn't do really anything, but it will allow for the second feature in a very specific way. So the second feature of the type system of Y is that types can compose other types, and you can generalize data structures like this. So you can have like an integer array, but you can also have, a pointer array. So the array type can compose, well, specifically the array type, the basic array type, composes another type. And that generalizes how it works. So of course the array type, each element is indexed, not as like each byte, like you would normally expect from an array, but you can do this with any type again, this type of composition is semantic. This is a specific thing, a specific reason about this, and it can be inspected at runtime if you need. Now, of course, I don't really recommend doing things at runtime if you don't need to, as we'll see later, with some of the other features. Specifically with efficiency, cutting down on things that aren't used. I like efficiency, but it's there if it's needed. And specifically, I should say, this type composition that I'm talking about is different from what you might think of as composition when it comes to types. In, of course, UML diagrams, you would have a HAZO relationship. This is not a HAZO relationship. This is a different compose relationship. I'll see a little bit more about this later. And the third thing, size abstraction. Basically, the basics of this is the matrix type. That's a basic type. Basically, when you compile, if you have constants there, it'll tell you if you messed up. And that's one feature of this, but it allows you to do things like the array type has its size, the length, as part of the type. And this allows for, well, of course, you get the compile time checking if you have a constant. But there's also dynamic allocation with that length that you have, but it's still part of the type, so it can be inspected at runtime. I mean, if you've dynamically allocated with a non-constant value, like say you take input from the user, parse it, and allocate an array with that length, then the length is part of the array type. So you can see that, and which means you can just give that array to a procedure, and it can just check the length of that array without needing, say, like a second variable in the classic C way, where you'd have a pointer to an array, and then you'd have the length of the array as another argument. You wouldn't need that if you just use an array type. So efficiency, optimizations are done on the semantics of a Y program, which essentially mean, okay, so if you don't know, most, or well, at least with C, and I would presume other compiled languages, optimizations, there are assembly optimizations that are done. So after the program is compiled to assembly, there are optimizations done on those assembly programs. But that, of course, only works for that machine, because that's an assembly optimization. Well, I should say that processor architecture, but in the worst case, that would be that machine that you're running on. But the optimizations in Y are done on the semantics, which allow them to be portable with some optimizations. And then also allow for some pretty powerful optimizations that would be quite a pain to actually program to find in assembly, especially without any restrictions on the assembly. When you're just jumping all over the place, it's pretty hard to. I mean, you could do it, but you would probably need giant data structures to keep track of things. But yeah, it's to make these powerful optimizations and portable. One of these is evaluating constant expressions at compile time. This, I mean, I wanted this for efficiency, but this also allows to get rid of macros. This language does not have macros. And you can simply use constant expressions. There are some things to deal with allowing constants to be assigned by the compiler for some things, but for the most part, you could have, I mean, for a very simple example, of course, if you have 3 times 5, well, actually, that doesn't even, that is a constant expression, but you can say, let's say, factorial of 8 times 12. If for some reason you needed that constant. Now, in other languages, you know, you might have at runtime, then it would call factorial, passing 8, and then when it comes back, it would multiply by 12, and then it would produce the answer. But that's at runtime, and that expression, you could calculate it out and just place it in there, but then it's, you know, you might have to put a comment to say actually what it is, but comments aren't part of the program, you know. Collapsing these constant expressions allows the writer to place some complex constant, say like have a procedure that calculates pi to some precision, and then, you know, I don't know, well, you can multiply it by 2 and get tau. But in any other language, well, I'll say most of the languages, that would be done at runtime. And even in the languages I'm thinking of, you still have to place something on it, like const expr in C++. You would have to place on a procedure to get it to actually evaluate at compile time. But at least as far as I remember, I don't think you can then use it at runtime. And that's the whole point of having this evaluation in Y, is that you can use these procedures at runtime or at compile time and mix and match whenever in your program. So I could have factorial of 8, and that would be collapsed, but I might call factorial of 3 later in the, or factorial of length, where length is actually the length of an array, or a value that the user input. So you can mix and match these, and it doesn't really matter. And as long as you don't add any keywords, it will just try to optimize and collapse these constants. And this allows for these macro-like constructs that I'll show a little bit later. And then, of course, any expression you have, you can turn it into a constant expression with a keyword. So if you need something to actually be at compile time, then you can just say, yeah, do this at compile time. And then a little bit of a note on efficiency. Type information, so all that stuff about the size abstraction and the type composition, all of that type information, plus the actual type information for which type it is, for a variable that you store. That stuff is only stored if needed. Obviously, if you just make a matrix, a giant matrix in a procedure, and you don't pass it anywhere, then you don't need any type information stored at runtime. So then I have a few examples here. I have basic types, some of the basic types in Y. Instead of going for some of the classic algo types that you'd have, say in C, I've gone for just calling things basically what they represent. Of course, technically, with these variables, I have natural, integer, and real. They can't actually, they don't store, infinite information. So they're still technically just however big, for your computer. Now, that's not exactly true, and we'll get into that in just a second. But for the bool, it's just a bool. It's true or false. Of course, I have natural numbers, 0 and above, integers, the naturals, and also negatives, and then the reals, your fractions, decimals. It's just the type, so whatever type the variable is, type name, and then you can also say equals a value. This is essentially in the same syntax as C. Type composition, so it's basically, I have a type, so I've got this natural type. I've got another type, pointer. Now pointer composes it technically composes dt, that root type that I was talking about before. So technically how this type composition works is that whatever type the type composes, so pointer composes dt, you can then make a variable with that type pointer composing any type that inherits from that. So I'm using the inheritance structure to actually restrict what composes where, because then also that allows you to do things on, say, in the standard library there will be a list type, and of course you'll have a resizable array and a linked list, and some basic data structures, and you could have, say, a list. You compose lists, and then you could say, oh, whatever it composes, you can call, a procedure on that type, but you don't actually, like, the list type is abstract. You can't make a variable that is the list type, that is specifically the list type, specifically has that as its type. But you could call the procedure on a variable that is tending towards the list type. I'll go a little bit more into it on the next. I think it's 2 slides down. But basically, it's just whatever type. So pointer composes DT. Natural inherits from DT, so you can make a natural pointer. But everything inherits from DT. So pointer, of course, you can have a pointer to anything. That's the whole point. Pointer P, of course, and it's equal to null. And this is a constant. I'm sure everyone who's used to C is used to this, but this isn't using any type of compiler trickery like C has to. I'll also have a complex type. I have a real complex, so I can have my nice complex number over here. Quaternions, so I have an integer quaternion, so I just have integers in here. Of course, you've got 4 values with quaternion, 2 values with complex. And then just here's a value by itself, because technically it's inferring that this is a real complex value because of this statement. But the value by itself would actually have the type with it. So you have a natural complex and 8 to 20. Size abstraction. So it uses bracket notation. I'm sure is common to most people with arrays. It's actually on the type though, as you can see here. A is our variable here, but the actual size abstraction is on the type array. This, of course, is a natural array, and whenever it's just 2 braces, that's going to, with the array type, initializes all the elements to 0. It's just whatever values the type has is just 0. So if I had a data structure and I did this, it would just be all the things in it would be 0. Now, as you can see, the actual basic number types that I was showing before actually have size abstraction as well. And this is the number of bytes that type takes up. So of course this is a 2-byte natural to have a size abstraction of 2 on the natural type. Now, by default, this is actually going to be your CPU width. So like I have a 64-bit processor, and that's 8 bytes for 64 bits. So it'd be an 8-byte natural if you just put natural, like up here. But you can change it to be any constant you want, even a constant that hasn't been defined yet, but can be collapsed with the constant expression collapsing that I was talking about before. And here's the vector type. Of course, this uses the size abstraction as well, so real vector. Just make some vectors really nicely without having to do much work. An integer of 1, so it's 1-byte integers now, and the matrix is a 2x3 matrix, and I just have it right here. I'm thinking a little bit about how I might I'm thinking about syntax a lot lately, so I'll be looking into this, but I think this is fine for right now, at least. I just have, braces within braces for this currently. So going on, procedures. Of course, I mean, most languages have procedures. A lot of languages call them functions. I would abstain from calling them functions for multiple reasons. But I'm looking into maybe including functions as well as like a function type. But I have procedures and a procedure type currently, and that's how we get pointers to procedures. I'll show that later. So of course this is declared and defined of a natural factorial, natural n. I mean, of course, factorial, and quick and easy base case. I mean, this basically looks the same as you would write, in your first programming course. And even if I wrote this into my program with that constant expression collapsing that I was talking about before, even just writing this, and then I could use this. It's nothing specific about like compiler functions. It works for anything that you can write as well. Now there are some signifiers that can help the compiler and also signal what the specific procedure's about. I didn't include that in here, but in this presentation, because it's only one more slide, I think. But I'll just say now I have a default. This is just default. This is normal C. It's a procedure. I can edit some global variables in here if I want. There's system, which is a signifier. The signifier is going before the type. Of course, this is a type, name, argument list. Before the type, you put instead system and then natural factorial, blah blah blah. Well, system space, I should say. It's of course spaced out. That would mean that the procedure can't edit any like global variables or anything like that. The only thing it can edit, I think I stated it's something like whatever. So if you have like a pointer and you pass a pointer to a system procedure, because it's intended for system calls, of course, then it could edit the data that is pointed to by that argument. And then I have math, which is basically a pure function. It can't edit any global variables. It can read global variables if they're constants, but it can't write to any global variables or read any non-constant global variables. Can't edit any arguments, stuff like that. And that one is the one that really helps out with the constant expression collapsing. Like this factorial, I should technically put like math, because I don't like have any other data. Like I'm not memoizing the factorials in here, so I should put math to make sure this is compile time. And then user-defined types. Now, currently in my design, I have two other abstract types that are below or above, however you want to think about it, DT, that root type. I have SDT and NDT. Intent is that SDT is for something you think of as one thing, and NDT is something you think of as multiple things, like the arrays and matrices, tensor type. Those all are derived from NDT, whereas pointers, natural numbers, real numbers, bools, those are all derived from SDT. And the type is pretty simple here. We just have the type name, colon, and then you can have one or two types over here. So if you have one type, so SDT, instead of inheriting directly from DT, inheriting from SDT. This is another thing I'm looking to exactly how I want to structure the basic types. I might go into some. This is obviously open to change, whether SDT and NDT stay or whether they're replaced with other things. But DT will be the base, the root type. So you can either have one or two types. If you have one type here, that's just what it derives from. So A type derives from SDT. And then, of course, I just have my member variable here, integer A. And, of course, if I wanted to access this, I would have, A type var equals, curly of, like, -5 or whatever. And then I could go var.a, and, pretty simple. And the difference here comes with composition and what it basically builds from in the syntax wise. Syntax wise, this builds from another concept I have, which are this abstract procedures, which I don't have listed here. But basically the idea is that you can have a variable that is of abstract type. So I could have a procedure that is, say it acts on a list, and it basically allows for much nicer compile time syntax. So like in the abstract procedures would essentially, well, technically, so with procedures, whenever you could, if you say collapse a procedure, it might sprawl out, so you actually like take the procedure and place it in instead of a call. And when it does that, it will obviously optimize what's in there. And with, say, a procedure that is working on a list, it would optimize that with, like if I was working on a linked list, I called it on a linked list, then it would optimize for a linked list. And this syntax uses these number signs. So the number sign refers to a type, an abstract type. And in the abstract procedure example, that would be a type from the argument list that is abstract. Like if I had matrix number 0, that would be basically the first matrix type that appears in the argument list. And that would be that type that is the same in that argument list. It's the same type as the parameter, well, I got the wording mixed around, I think. But in the parameter list, you have that type. It would be that same type from the actual argument that is passed into it. It would optimize for that. And so that happens with the type composition as well. So here I have B type, and since there's two types, the second one is derives from. So it derives from a type. So obviously it still has this integer a within it, but it composes on STT. So only STT and things that inherit from STT can B-type compose on. But of course, with a normal variable, if you compose on STT, which is an abstract type, you wouldn't be able to do that because it's abstract. If you have abstract in this type composition, then you can't actually make that unless you're in one of these abstract procedures or here in a type that uses type composition, like here where I have STT number 0 or b. So I have a variable b that is of type STT number 0. So that is saying that it is the same type that's used to compose on B-type. So if I had real B-type var, then its B member variable would be a real number. And if I had an integer B-type, then its B member variable would be an integer. And so that's how this type composition works. It uses this syntax for abstract types to assign which abstract type is it talking about. So in type composition, that abstract type is, most likely the type that the type is composing. And in abstract procedures, that would be something from the parameter list. So I think that is a decent brief interview. Like I said, this is quite brief because, especially when it gets into this type composition and the abstract procedures, might get quite long at actually describing how this works. But the type composition, you can have, you can keep going with it. As long as the type composes, then you can keep going with more type names. Like, you can have an integer pointer, 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 pointer. Because pointer composes anything, and pointer itself is a type that inherits from DT. So you can just keep going with pointers and just have pointer, 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 with something before that. I should say, technically, if the type composes something, you can't leave it blank. So I can't, with B-type here, it composes on STT. If I left it blank when I tried to make a variable of it, like B-type var, that would give you a compilation error, as well as giving it like array. If I gave it integer array B-type, that would also be a compiler error, because, like I said before, array inherits from NDT, not STT. But I think that should be... Well, this is all of the actual presentation. Let me move the... Well, let me get rid of the actual presentation real quick. Because that is the end of it. And let me open a text editor real quick. Oh, yes. Let's see. OBS. There we go. Now I should be on. Let me try and full screen this real quick. There we go. Don't want it to take up less than the full screen. So now I'm in Vim. If you heard of Vim, it's just a text editor. It has some nice features that I'm using here. Like, I've created my own very simple syntax highlighting. I've basically just said, oh, here's the types, and then it will highlight those. Constant, it highlights. It doesn't seem to do the job for everything. I don't remember if I made allocate, because allocate is a keyword. I'm not sure if it's in there. I mean, I guess I could check real quick. Oh, I hit the wrong button. Nope, it is not a keyword. So I don't have it finished, all the syntax highlighting, but also in some cases it doesn't like to work. I should say right now that rand, I'm just using rand right now really simply, just to be like, here's a procedure that returns a random number. The actual, I'm definitely going to have some type of random number generator, well, multiple, probably. But it's probably not going to be like this, and also it'll be in the standard library, so it'll have to be called, with a library. I should say right now, before I do anything, I do have libraries. I'm calling them libraries. They're namespaces. Very simply, library. I don't know. The lib. It's namespaces. And then you can create types and add in that A type from before. A type, what it is, SDT. Integer A. I might as well add in B type and show off the type composition a little bit more. SDT A type. It's just SDT number 0, and then B. So yeah, it's just a library. It's just namespaces. I'm still not sure whether I'm actually going to use deallocate or free. So take this with a little grain of salt. But this example actually is about allocation. So say I have an integer array here, 3, and I have my array here. So everything here would, for efficiency's sake, would compile down. As long as I don't give this to any procedure. But even if I do give this to a procedure, if that procedure has, say, like, it takes an integer array 3, then no type information needs to go. It will just send a pointer. You won't need to. Essentially, the point is, if it has the specific concrete type, then it can do the compile time checking in that procedure. It doesn't need to do that. It doesn't need to add type information to do runtime checking. I can also just make a bare array here with just a pointer, a constant pointer specifically, pointing to some array. And so this is, of course, my random number. And this is just to show that at runtime, say if I could get this from a user or anything, it doesn't really matter. I could have a pointer allocated on the heap with allocate. Well, this is an array, I should say. It's still an array because I'm doing allocate of that length integer. So I'm allocating that many spaces in the heap of size integer, which of course on my system it's 64-bit, so that's 8 bytes. So it'd be, you know, length times 8 bytes allocated. And then an array, the array type allocated on the heap. I have integer array pointer. Now notice I don't actually need the size abstraction here on the array whenever I have pointer. Pointer is a special type in that how I said before that all the types here need to be concrete if you're going to make a variable of it, unless they refer to something in abstract scope or something like that. But with pointer, they can actually be abstract, as in this one doesn't have its size abstraction. So if I just said integer array r to make a variable, like, I should just write it since I'm here. Integer array r. This is a compiler error. This is a compiler error. You don't have the size abstraction. The size abstraction is necessary for any type that has it. So this would give you a compiler error. You would have to have of some constant, like, even though it's not really. I mean, this is an example, so it doesn't really matter what I put in here. But this is a constant CPU width, and that's the constant that actually goes with integer and pointer. The integer, real numbers, natural numbers, those all default to being CPU width. Because those types, at least right now, I'm thinking of just having it default like that instead of having you actually. I might open the default, having a default number to other types for the size abstraction, but I'm gonna think about how to do that syntax-wise and other stuff. But so like on my system, CPU width would be 8 bytes, because this is in bytes, CPU width. Now, this ties into the portability aspect, because CPU width is a constant that is supplied by the compiler. As in, the value is supplied by the compiler. Whenever you compile it, you can set it, but the default, of course, would be whatever system you're targeting. So with my system, B8, so I'd have an 8 long array of integers. So this would be, you know, 8 integers that are 8 bytes long, so 64 bytes. But yeah, with this, without the size abstraction, this would be a compiler error. Because even if I open defaults to other default size abstractions to other types, it won't be coming to an array. At least I don't think. Like I said before, deallocate. I'm not quite sure if I'm going to use that, but so these allocates up here are allocated on the heap, like malloc in C. And deallocate then is like free. And like I said, I might just name these free. It's similar. It's also similar to new and delete from C++. I won't get into specifics right now, but as you can see, allocate, which is a keyword, this is like a built-in. It takes a type, as its argument. And then, of course, with deallocate or free, whatever I call it, it just takes the pointer. So any pointer you put in there. So then I have these. I have these types down here that I supplied, and let me write out a little bit of. So the lib, syntax-wise, I'm thinking of this right now, but okay. So I can have variables of these, of course. I don't know. I'll say at, and I can just go at.a equals -5, and I can also have, say, variable b type, and now this would give a compiler error because I haven't composed the type. So if I say copy this to here, I'll leave this line up here because this is a compiler error. Let me now do the correct thing. So anything that composes STT, it's like the natural type, and I'll just use natural for right now. So I have my natural B type. Now this, I'll use it in just a second, but I will also place back here. So anything that composes NDT would be an error. So I'll say a natural vector of 3. Vector, of course, inherits from NDT, which inherits directly from DT, so it never goes through SDT, so this it does not inherit from SDT, so this would also be a compiler error. So I will also place that over here. Compiler error. Okay. And now that I have the correct one, so the correct one, of course, here in the middle is the actual one that works. And I can say, bt dot b equals I don't know, 4. But bt dot b equals -6, and that is a compiler error. Or I shouldn't say compiler error. I should say compilation error. Or compile time error. So since -6 is an integer, and of course you can't assign integers to natural numbers, just like that. Now, if I casted this, I could assign it, but it isn't cast, so it will give an error. then, so like I said, so work like this. I'll have a, like I was saying with this type composition earlier in the slides, then I could say, you know, have a real B type I'll just name it RBT as an example, and go ahead and go RBT.B equals, I don't know, 3.92, and because composing on the type real, then B here, this STT, first to what it composes to, composes real, so B is real. And that is at least a tiny example of, well, further of how type composition works, but also on allocation, at least a little bit. Like I said before, these deallocates, these might become free. Let's see. Those are also built-ins. And then libraries, of course, namespaces are nice, so. And the namespaces, you know, of course, these are anything that can go in your normal global space can go in there, essentially. There's some more specific features of, I mean, all of these things that I haven't gone into, like stuff like you can only, like this library, I've got this type, I can see the types and the procedures, but and constants, but actually variables that are inside here can't see. I say C, of course, you know what I mean about scoping rules. So you wouldn't actually be able to access, read nor write, if I say put, I don't know, natural N. Well, I'll just say natural N. Yeah, that would also cause compilation errors. I mean, it doesn't matter what I do on this line. There's an error. But like I said, there's lots of other features that are smaller that I didn't really want to get into on such a brief overview of these concepts. Because I mean, especially with the abstract typing, this is and the type composition, this is a complex feature. Like what I can do, integer for pointer matrix pointer vector2 v. There we go. So I can just keep adding types, just keep adding, well, technically I'm adding, the actual type of the variable. So it's like v here is a vector that composes and, this type over here. If I get out of insert mode, wrong way. So vector of 2 composes all that stuff over there. Pointer, of course, composes all this stuff over here, and basically it just recurses back. Pointer-wise, it points to the other type and points to the other type in the actual compiler, but so I could keep changing the type, and say now it's a pointer, and I've added another type name to this list. Of course, now I can, like I was saying before, I can keep adding pointer, and it's still, this would compile. Of course, I'm making up weird examples that you probably wouldn't use, but it's a complex system, so no matter what you come up with, you can, make it happen. And also, I should specify just before I go that the array types, the array, or the matrix as well, vector, these types actually they actually change in size based on these size abstractions. Not just like how the integer 4 would be 4 bytes of integer, but also that if you like dynamically allocated a vector, the reason it's semantic and that this is part of the type is that then your data structure is actually variable in length, which is not really a thing elsewhere. You just have to have a pointer to point to the rest of the data instead of having an actual variable length data structure. So I think that's going to be it for my example. I guess I could check to see if where do I have the first workspace. If I look here to see, do I have any other examples here? Oh yes, I'll show this example quite quickly. Let me, yeah, I'll just save this. Quit vim procedure. So really quickly, let me show my syntax for, I will show the syntax for procedures, because this is quite important. This is a procedure. As in this, well, this is a procedure variable. I'm not going to get into it right now, but this is the syntax. If I had this and then pointer after it, it would be a pointer to a procedure. But that will be all for me today, and I will be back another time. Thank you, and goodbye.